Okay, let's talk about causes of isotope variation. Okay, my goal right now is to review and simplify. This is what Jim always talks about, give you the rules, okay? So this one should be simple. Carbon isotope variation is a function of source, supply, and demand. Jim did that a lot yesterday, right? The supply of CO2 associated with stomatal conductance, the demand associated with photosynthetic rates. That's what's going to drive the changes in CICA, right? CICA, which is going to affect a carbon isotope discrimination. So there's other things. There's post-photosynthetic fractionation potentially, but cellulose is a primary metabolite, and there's very little post-photosynthetic fractionation at that point. Or you can talk about retrieval from storage. I'm going to delay that. We'll talk about where that might be interesting a little later when we talk about subdivisions. So having those basic things in mind, do these data sets make sense to you? So here is some work by Kristen Treta that looks at, this is the raw data, the black here, over time. Look at that drop, an amazing drop. The climate's changing dramatically. Wait a minute. First thing she had to do was what? She had to correct for the isotopic composition of atmosphere, because the isotopic composition of the atmosphere has changed. So that's the blue line. And then there's also changes in the parts per million, the actual amount of CO2, and she corrected for that. So this is now her corrected value. So what is she correcting for? Source, right? She's looking at the source change and how to correct for that. So you should always know about that, especially going back farther in time. Okay? What about this study? What we have here is a precipitation index, and this is a reverse scale. Be careful of that. This is a reverse scale. So this is high, low, and this is the carbon isotope ratios. So when you have high precipitation, you have low carbon isotope ratios in the tree ring. Does that make sense? Okay, think about it. High precipitation, lots of water, high humidity. What will you do with your stomata? You open them. If you have an open stomata, your supply of CO2 is good in 2. So your CICA ratio is closer to 1. Therefore, there's more discrimination. More discrimination means you're discriminating against the heavy isotope. That means your isotope becomes depleted, more negative. Right? Did that make sense? You want me to do that again? Okay. So that whole thing should make sense. And there's another one here, moisture index and carbon isotopes. These are all tree ring stuff. You can do the same thing with leaves, but we're talking about tree rings. Jim talked about leaves last time. Debbie Hemming did a nice study with vapor pressure deficit. She's reconstructing VPD over hundreds of years. Why? High humidity. Plants tend to open their stomata because you don't lose as much water. You open your stomata, again, the CICA ratio changes, discrimination. You see why this makes sense? Okay? This is some work by Steve Levitt that's looking at these decline over time. See how these are almost all going down? This is an indication of intrinsic, remember Jim said, intrinsic water use efficiency over time, and they're looking at pinyon pine and so carbon isotopes. So there's been a lot of work on tree rings and how intrinsic water use efficiency has changed over hundreds of years, and it has increased. Here's one from an eddy flux tower showing the discrimination, and this is water use efficiency, and they're related in the tree rings. So we can use tree rings to look at water use. And finally, this is some work that I've done in 2012. This is photosynthetic rate in a controlled experiment with 2 species. This is the control, and then I gave them low light, and then I gave them low nitrogen. So low light, they have a lower photosynthetic rate. Well, duh, right? But low nitrogen, you have less enzymes, you can do less photosynthesis. So both of these reduce the photosynthetic demand for CO2. Now, all 3 of these had no change in stomatal conductance. Stomatal conductance was the same across them. So there's no change in supply, but there is a change in demand. What happens to the carbon isotope ratios? They become depleted, right? Because if there's less demand, the CICA ratio will be closer to 1, and you'll get more discrimination. Yes? Give me some nods. You guys getting that? All right, so, and Jim said to a lot of us in a lot of groups, when you're sampling a tree, you should be knowledgeable where you're sampling that tree. Is it a shade tree, sun side? Remember he talked about that? Because it's going to make a difference, the demand side. Okay, let's review and simplify for oxygen isotopes, or on hydrogen as well. So the three big things are the source of water in those leaves, what is going into the tree, okay, the 18O or 2H value. The atmospheric vapor, delta 18O or 2H, related to the source, and the evaporative enrichment driven by VPD. There are other things that we could talk about. There's some biochemical fractionation. Is that constant or dependent? Proportional exchange, constant or dependent? There's some issues about that, but most of those are very minor changes, and there's other things as well. So these are the big three that I think you should think about first before you think of anything else. Okay, so do these following data sets make sense? Carbon isotope ratio, oxygen isotope ratios in a tree ring is a function of humidity. Should be, right? Evaporative enrichment. The higher the humidity, the lower the evaporative enrichment. The lower the humidity, the higher evaporative enrichment. And that is translated to the tree ring, not just in the leaf, but into the tree ring. And there's another one, humidity and delta 18O. What about, this one's interesting. There's a couple of, this was ice core data of temperature. So this is the Younger Dryas event right there. And this is willow remains that also see that Younger Dryas event. This one's looking at temperature over these years, and this is the deuterium content sort of matching it. These guys are estimating temperature. So again, remember, one of the first things people were interested in is using tree rings as a paleothermometer, and it does record temperature. Why? Because of the condensation temperature, the source water value. So this is a feature of source water. The source water is changing. There's some other features as well, but this is primarily a source water change. We can get temperature. What about precipitation amount? And so here's a study by Jim White. This is the May-August precipitation and mirror image, is the deuterium. This is some work out of my lab with Jim Johnstone that looks at summer fog and rain in combination as a relationship with delta 18O, and we've got a pretty good relationship. So the more rain you have, okay, the more humidity, the more water source you can have, more the evaporative enrichment can change, the source water can change. So this is a measure of precip. We can get those information. And one of my favorites is done by Ed Wright, because I've never seen this good of a correlation anywhere. Back up, or this one? PDC, Palmer Drought Severity Index. Yes. Yes. Yeah.
So how does that match up? Does that help?
Actually, most of that PDSI is done with carbon isotopes, but water isotopes can also be affected by that. I'm not seeing as much work on it, but yes, integrated values of water source. But it's not as clear. I think it's clearer in some of these because of the location. The location in your location might not make a difference. So you have to be careful. This is not an all-encompassing truth that precipitation will affect it this way. It's always site dependent.
But wouldn't that be the utility of using some index that incorporates both of those measures?
Sure. That's why we're doing. We didn't have as good a correlation with just rain. We didn't have as good a correlation with just fog, but if we look at them both, now some of those indices are even more complicated. But yeah, those things are good.
Can we have the same application similar to the fruit, the crops of the tree?
Yep. So all that I'm saying to you today applies to non-tree species of plant in particular. So any crop species.
No, I mean the similarity between the leaf and the fruit.
The leaf and the fruit? Yes, you can almost think of the fruit as a product of the leaf, and so it's almost like the tree ring cellulose. It's getting that information, and there might be exchanges when you're making it. But how much is cellulose, how much is other kinds of carbohydrates?
No, my concern is only about the matrix itself, because in the fruit we can find acid, we can find much more than cellulose. So it might affect the fractionation of deuterium and oxygen.
Yeah. So you can only use the model we've been talking about with cellulose. Only cellulose. If you start saying, I want to look at sugars in the fruit, you have to now do a different model system. But the basics of applied for the evaporative enrichment and everything else is valid. Okay? All right. Yes?
Wouldn't you need to know more about the stomatophysiology of a species or functional group to get at exactly how much enrichment is happening?
You'd be surprised that it's not as important as you think it is.
Okay. So
Partly because.
At what scale is it important?
Well, what we should do is you go to the model and you play with that. How much do I have to change tomato conductance before I see a change in leaf water and stem cellulose? And you'd be surprised. Part of it is because it's a steady state model. And whenever you deal with steady state models, those kind of perturbations are sort of washed out. If you look at the non-steady state models, and then you see diurnal changes that are more important. So then you need to go to Lucas Cernacek's papers, and it gets more complicated. But again, I want to reiterate, the steady state model is giving you 90% of your variation. So if that's not good enough for you, then you need to go beyond that. So, you following me? Does that make sense? Okay, so here's the correlation with post-fall slatewood ring cellulose and Tucson precipitation, R of 0.9. Wow, I've never seen that. I mean, in some tree ring width analysis, if you get an R squared of 0.3, they kind of go, woohoo! I got, really? But isotopes can even be better. And he's relating the variation in the precipitation to El Nino monsoonal events. And so he can go right back to, and there's a delay of about 11 to 15 months of certain things. And so it's a very nice monsoonal precipitation event. Okay, questions?